My talk is about Readyset and what we call it to be a new era for MySQL caching, but in its database caching. For the ones that don't know me, I don't have a funny picture like the other two speakers, so I missed the memo. My name is Marcelo Altmann. I am a senior software engineer at Readyset. Recently joined it like 3 weeks ago. Previously, I was a software engineer at Percona. You may know me as the maintainer of Extra Backup. Did some good work there, like Arnold was telling, like the standard, FIFO, data sync, and other things. A long time MySQL community contributor with blog, talks. Also a MySQL code contributor. Oracle has been queen enough to accept some of my contributions over there. Our agenda for today is just give an introduction of what is the problem we are trying to solve and what is the current landscape of caching in MySQL. Then I will show how Readyset tries to solve this problem statement, and I will have a quick overview of how you can deploy Readyset. So let's start from the basics and recap what is a cache. So basically, cache is a piece of software or hardware that you store some data to be served faster in the future. Caching something is just half of the problem. The big problem comes later, which is cache maintenance or cache invalidation. At Readyset, we really use this code from Phil Carlton a lot that says that there are only two hard things in computer science. The first one is cache invalidation, and the other is naming things, which is true. When you cache something, you save that information in memory, but later you have to decide what you have to do with this information. Like you will let that entry result set be in memory forever. Are you gonna put an expire date on that? Are we going to build something to update that cache, or just invalidate and evict that particular entry? Coming to the MySQL landscape, who here remember query cache or have used it? So query cache was deep on this particular problem. If you remember, you could specify an amount of memory for MySQL, and it will automatically cache entries. And the big problem that MySQL query cache had was exactly with cache invalidation. There was a single mutex that will lock that particular entry, and every time you had any DML, like any data that will modify, you will have to check that memory to see if it will have to invalidate something. And these caused problems with concurrency, reaching to a point that query cache was not giving you any performance. It was actually doing the opposite. It was just dragging your performance down. If you remember, you will do a show process list, and you will see queries in waiting for query cache lock. So that was exactly this. It was the query, the cache invalidation part of the MySQL query cache. I think it was query cache was then deprecated on the 5 series, and it never reached 8.0, right? Mm-hmm. It was removed from 8.0. We also have InnoDB buffer pool, which fits the cache analogy here. It is an area in memory where we save raw pages to be later served faster. So once you have a page in your buffer pool, you don't need to fetch that from disk again. But here we are talking about raw pages, and any computation that you have to do, like aggregation or joins, they have to be done over and over again because you are just storing the raw pages there. So only half of the problem is being fixed here with InnoDB buffer pool. Then we have ProxySQL here. We have the representatives over there, which among other things, it does query caching as well. Like you can configure a query rule that will cache the result sets that you have. But ProxySQL utilizes the concept of TTL, time to live. So once you put something in memory on cache, it will be valid for a specific amount of time. Let's say you put 10 seconds. So you have that cache entry on 10 seconds. After 10 seconds, it's guaranteed that you are going to have a cache miss. You'll have to fetch that information again. And also with the problem with ETL is that if something changes in the underlying data, it's guaranteed that you will be a stale read for the duration of the TTL. And the other thing that we have in this landscape is external tools like Redis or Memcache that they are built and meant to be cache of everything. Drawbacks with those type of software is that you have to configure your application to be aware of the cache. Normally what you have to do before you go to the database, you have to be aware that there is a cache there. You have to check if the information is in cache. If it's not, you go to the database, save on cache, and then later you can serve this information from the cache. But those tools, first, it requires you to do application changes. When you store something on cache, it's again TTL based, or you can never expire an entry, but you have to build the tools around your application to keep that cache up to date. You have to do a batch process that will fetch all the entries on cache, go to the data store, see if that entry has been updated, and all this burden, all this maintenance, it's shipped to the side of the application. So now that we understand what's the problem we are trying to solve, I will present you Readyset. Readyset, it's based on an MIT PhD thesis, which is named Partial State in Data Flow-Based Materialized View by John Jensen. Some people also know this by Noria, which is the implementation John did while proving his thesis. John, the thesis author, is one of the co-founders of Readyset. Readyset is source available, so you can go to GitHub, compile this by yourself. It is licensed under BSL, so unless you are doing a cloud offering that uses Readyset as the core product, it's free to use in as many instances as you need. We divide the product kind of in two. We have the core, which is the software. It's what this talk is about. But we also have like a cloud offering, which is a platform for database caching, which in a few simple clicks, you can deploy Readyset. So what appeals to Readyset is that it does not require any application code. It's a proxy that you put in between your database and your application. It talks the MySQL and the Postgres protocol, so it requires no change. The only thing you have to do is change your connection string to Readyset. It does automatic cache maintenance for you. So if something changes on the underlying database and you have that entry in cache, it will be automatically updated in the cache. It does horizontal scale, so you can boot more Readyset instances in order to increase like the amount of entries that you can cache. So how Readyset works? There are three main components that I will be talking here. The first one is snapshotting. So Readyset, when it starts and it sees that it's booting a new instance, it will snapshot the data that you are trying to cache. Here, tables. You can snapshot all the tables, or you can say, I just want to cache on table A, B, or C. It will do something super similar with what MyDumper does, which puts a lock just to start a transaction and have a consistent view of the data. And then it will do by batch. It will be purging the data, collecting the data and saving in the Readyset side. Readyset uses MyRocks under the hood. So we know MyRocks uses RocksDB. We know RocksDB as MyRocks in the MySQL world, and we know that it's super optimized for space. Once this snapshotting is done, Readyset registers itself as a replica. It does like change data capture. So basically, it's gonna be your, let's say, read replica, your cache replica, and it will be informed when something has changed in the underlying database. The next thing is the core of the product, which is the data flow graph. To explain what a data flow graph is, I will be using an example query here, which is a select on a stories table, that it brings the ID, author, title, and a number of votes that a story has. It will be joining these into a votes table, doing a count of the number of votes each story has, and it will join those two tables together, and we will always have a story ID as a parameter. This is a visualization of what the data flow graph will look like. In blue here, we have the tables that we have snapshotted, and we call those base tables. So each base table will be the root node of the graph, and each base table will have an outgoing edge to a second node in the data flow graph. And those nodes here in green, they are, we call like the operation nodes. Each one of the nodes, they are responsible to do some operation. So on our select, we will have this aggregation node up in here, which will be responsible for doing the count of the stories. So here we can see that it's grouping stories 1, 2, and 3 and counting all the votes that this story has. It will then have an edge to a second node, which is the join node. The join node, as the name says, it is responsible for joining the data from the two tables. And the join node will also have an incoming edge, which will have a parent from the story table, which is the one responsible for populating the author and the title of the article. So here we have the data that we need, and then we will have the leaf node of the data flow graph. It's going to be what we call the reader node, and this is the node responsible for answering the questions and queries that we have. If we look the data flow graph, how it is right now, it is not super optimized because we are actually materializing every single entry that we have on the base tables, the votes and the story tables. Then it comes to the third part of the Readyset, which is what we call partial materialization. The data flow graph will only be populated with entries that have had a cache request. Like here, the example is that we only have the story ID number 2. So this is how we optimize memory usage, by only partializing, materializing the entries that have ever received a cache request. This brings us to cache misses. So what happens when you hit a cache miss in Readyset? What's the workflow? What has to be done? So here we have an example of a question for story ID number 3. As I mentioned, the reader node is always responsible for answering the cache requests. Here we will do a cache request on the reader node, and we'll see that we have a cache miss. And then internally, Readyset will do what we call an up query. We'll have to traverse the data flow graph and query our parent to see if that data is available. So here the reader will have to go and contact the join node in the graph to see if it has story ID number 3. In this case, story ID number 3 is also a cache miss on the join node. So the join node will have to contact its parent. In this case, the join node, it has 2 parents. So utilizing some heuristics, it will choose one of the parents, but we will have to call all the incoming nodes recursively. So in this example here, it will first contact the aggregation node. We'll see that also there is a cache miss there. And then we'll have to go and eventually query the base table, which there are 2 things here. It's either guaranteed to have that particular data if the story ID number 3 exists, otherwise it's a null and it's an entry that does not exist. In this case, the story ID number 3 exists. It will then project that information back to the count node. The count node will be responsible to do the aggregation. The aggregation is done. It's sent down to the join node. The join node sees that it has not all the information that it's required in order to answer the question. Then it has to recursively call the other incoming nodes, in this case, the story base table. We will then, the story base table will be the one responsible for projecting the data of author and title. And then eventually we will get to the reader, and then we are able to answer the question for ID number 3. And then right now, reader has the information from ID number 3. If some question for ID number 3 comes in again, it will not be a cache miss. We will be able to answer right directly from the reader. Cache maintenance, how it works. Because Readyset registered itself as a replica, it knows when something has changed in the underlying database. Once we receive a binary log entry for one of the tables that we have snapshotted, it will trigger a data flow action, which is to send the delta information, the information that has been received, to the nodes in the data flow graph. Like in this example, Marcelo has voted in story ID number 2. This will trigger an action to send this data to the aggregation node. Let's say the aggregation node does not have any, it has not materialized the ID that we are receiving here. Then the workflow ends there. It will not go down, because if the aggregation node does not have that information, it means that down the graph until the reader node, that information is also not required. Here, in this case, we have, so we changed the votes count for story ID number 2 from 20 to 21. That information will also be propagated down to the join node. Join node will do the exact same thing. Since this is just a maintenance, we don't have to do anything with the other incoming node here. The only thing we have to do here is to project that information down to the reader node. That done, if someone comes and query now story ID number 2, it will have the updated information like it is in the database. Stale reads, it's not just wins. Readyset also has, if you want to use Readyset, you have to tolerate stale reads. There is a time in between propagating this information down to the reader node that someone can come and query the reader node for ID number 2. If this happens, you will be actually serving a stale read. In this case here, in the database, if you query in the live database, if you query the exact same query, you will be getting 21, because that's the live information. But that information has not been propagated down to the reader node, so your application has to tolerate stale reads. It is eventually consistent. Eventually, the data will be consistent in the reader node. And a caveat here is that this is basically what any asynchronous replication, any asynchronous system has. If you already has a split of reads and writes in your database and MySQL, you already are facing this same issue, that it might, your data might be stale.
Are there no options to choose to read, to wait for the data to be updated if you see it's stale? Because that might be depending. I mean, in theory, in some cases, maybe you don't care. But if you do care, then you might want to be prepared to wait for the materialization to come through, rather than getting stale data and not being aware of it.
Right. There is some work that it's been done with GTIDs. Basically, what ProxySQL does with binlog servers, the same thing that like we track what was the GTID of the last write, and we only serve the cache entry if the cache entry is updated up to that GTID. It's in the roadmap. It's not implemented, but it's one way of solving this problem. It introduces latency. Then
sometimes you care about latency.
Yeah, or
speed, and the accuracy is not 100% necessary.
yeah. Other thing that happens is that the up query, the cache miss that I was showing, there is an option that you can choose to, in the background, do the up query, but proxy that information, that same query, to the database. So you don't have to wait to the materialization to come down to the div node. You will query the database, do the query there, and then eventually it will be there in the reader. That's the other thing we were kind of.
But if you base this on GQID, isn't that pretty coarse information? So, for example, if you are reading for ID3 in this case, and there's no update going on, you will still have to wait for the update on 2 to.
Yeah, there are two things here. One is stale read, which is this case here that I will be serving 20, while it should be 21 if I would query the primary database. These can be solved with GTID. The other one is the latency in when you have a cache miss. These we have the option to redirect that a cache miss, do all the workflow on the data flow graph in the background, and the query be redirected to the primary database.
But the GID, the user of the GID wants to solve the problem of reading their own data.
The stale reads, yeah, that's what.
But on your own data, like if there is another connection that has increased the count for ID2, for example, you won't be able to see, like you don't know that there is data with.
Right. It will only guarantee that you are seeing the same data that you have written. I believe it's the same thing with proxy SQL, right? Yeah. You cannot know that I just inserted some data there, you inserted. There's no way I will know that you inserted unless I start a new transaction or something. Yeah.
Is the reader leaf actually only updated when the user is requesting data and synchronized with the join data?
You mean
The reader leaf, yeah.
if I have ID number 2 here, there is a guarantee that we know that if I have any entry, guarantee that this entry is there.
So no matter if a user requests or not, it will be updated eventually. The reader leaf.
Yeah, the entry will only be here if someone had requested. This is the partial materialization. Like for example, story ID number 1, it's not here because no one has requested. So if there is an update in story ID number 1 here, it will hit this node here and it will see, I don't have story ID number 1, so I will just discard this delta. But if it's something like in here, story ID number 2, it means that yes, someone has requested and story ID number 2 is materialized. So I need to do all the workflow until
so in order to trigger the data travel from the node to the reader, you need to first have a request from the user.
Yes. It means that you need to have a cache entry for that ID. If you...
But what if we have, for example, 100,000 rows in this case? So you will have the original tables, but the whole process on the right, the data flows, will not be updated unless the user actually requests the data, right?
Correct.
So you might have a very small data set in the reader leaf or the join.
Yeah, this is what the partial materialization part does. Like it does not populate the data flow graph unless there was a request.
And that should just happen in order to have a smaller, let's say, overhead.
Yeah, you don't want to, let's say you have 1,000 users. We are doing logging kind of thing. You don't want to cache the 1,000 users if you have like 5 hot users that will be, or stories, 5 hot stories that will be queried more often. So it's a waste of memory, this other 900 entries to be in memory.
So you're expecting a cache miss in order to start.
Yeah.
Okay.
Yep.
Or you warm your cache.
Yeah, or you can warm your cache.
In case of cache miss, how is the cost for fetching the nodes up to primary?
It's latency. You don't have to go to...
The latest you can join and the cache node, how do you measure? So like there's a measure for that. So like for example, it's 1 millisecond between the reader and the join node, and 1 millisecond between the join to the group.
You mean to choose between going to the primary database or answer from
Yeah.
the graph? It's a user configuration. You have to choose. In a case of a cache miss, you want to do an upstream query, or you want to
so
wait.
like for example, if you're waiting for 10 milliseconds, so it's just like, oh no, I'd rather go to the primary rather than wait for 10 milliseconds.
Yeah, but that's a user decision. It's a configuration when you boot Readyset to say, in cases of cache miss, I will do the background process and wait, or I will do the background process and proxy the query.
Go on.
Yeah, I have 5 minutes and it's just one more slide, I think.
Yeah.
So Readyset architecture, this is kind of workflow of how it works. We divide the binary in two, and you can deploy in standalone mode where adapter and server, they are in the same binary. Adapter is the one responsible for reading the queries, the Noria adapter that we have here. It reads the queries, and it decides if it's a write, it redirects right to the database, because we don't do anything with writes, we receive from the replicator. And if it's a select or a read, it will validate if it is something that it's cached, then it will go and go to the leaf node, which is the reader. And the reader node, the leaf node on the data flow graph, it resides on the adapter. Then we have the server part, which has the rest of the data flow graph. It's where we store the base tables, and it's where the replicator also resides, the process that it's responsible for snapshotting and do the change data capture. But you can also deploy Readyset splitting into different binaries. For example, the adapter, you can split and put the adapter close to your application, and it lets you do some sort of CDC, for example. CDN. Like, let's say you have US and Europe part of your application. So with this, depending on the access pattern that you have on those two sites, the leaf node will only contain the entries from that particular site. For example, here we have story ID number 1 and 3, while on the other adapter we only have materialized story ID number 1. So it lets you horizontal scale your cache by splitting the adapter into multiple processes. So in summary, Readyset is wire compatible with MySQL and Postgres. It requires you no code changes, so it's just plug and play. And it's cool because it automatically does cache maintenance for you. Give it a try. You can go to our GitHub if you like. Start us, blog about us, tweet about us. We are a startup. We are starting, so we like to get feedback. We have a Slack community if you want to ask questions more directly with the engineers. Here are our handles on Twitter and LinkedIn. In terms of deploying, Readyset it's written in Rust, so you can either compile by yourself. We have Docker images and Debian packages. Last but not least, I know we have a community dinner tomorrow. So if you can still drink some beers, we'll have a happy hour on the Delirium Cafe Saturday at 6 p.m. So I hope to see you there. And that's it. Thank you.